Bonjour. First of all, I would like to thank Professor Clément Sanchez for his very kind presentation and also for the superb organization together with the organizing committee of this colloquium. Professor Sanchez is a real model, so energetic and so capable, of course. And so I hope this is going to be, well, the beginning of a long-term collaboration between Collège de France and Colégio Nacional, especially in the area of chemistry. And Professor Sanchez will be coming to Mexico next month and will visit several universities in Mexico. For example, I don't know if any of you has been in Guanajuato. So it's a picturesque city, some 300 kilometers northwest of Mexico City. And in any case, I hope that you will have a very nice stay. And for me, it's a great honor, of course, to interact with you, a very emblematic group of chemists in France. And so I'm really honored and fortunate. I would like to mention that some 15 years ago, I met this beautiful woman, Professor Janine Cossy, in Nagoya at International Conference on Organic Synthesis, organized by Professor Hisashi Yamamoto. And then yesterday in Orsay, I met a true gentleman of chemistry, Professor Vincent Candon in Orsay. So hopefully today I can meet many more of you, and very much looking forward to hosting you in Mexico as well. Okay. This well, this slide includes well, what you know, the green chemistry has been getting the attention of many chemists in the last 25 years or so. The definition might be something like green chemistry refers to the design of chemical products and processes that reduce or eliminate the production of dangerous substances for the environment or for human health. I have to admit that for some time I had the impression that this slogan was kind of a bit commercial. I mean, in the sense that I said if somehow I can get these terms into a research proposal, then perhaps my chances for getting support from CONACYT in Mexico, might be improved. But then, in 2010, I read a couple of editorials, one by Professor Anastas and Ekbali as co-author. This a very nice article in Chemical Society Reviews, 2010, and then a short editorial by Professor Noyori in Tetrahedron. And both of these articles essentially said, if we are not able, as chemists, if we are not able to dominate green chemistry, then there is a real danger for humanity and for us, even for us as chemists. And so I said, well, if these people, these important people say something like that, maybe one should pay really more attention. And so that's when we decided to try to do something in this area. Some of the areas of importance in green chemistry concern the use of renewable starting materials. As I said, they having chemical routes that will have no environmental impact. And then today I will be talking a bit more about substitution or, why not, elimination of the use of solvents or potentially toxic solvents in chemical reactions. Of course, we want to develop safer chemical products and processes. And then today I will touch also on the potential application of more efficient energy sources. As I said, this is a fairly recent topic, but for example, beginning the year 2000, 2010, we have a series of books and journals. There is one more missing here from the American Chemical Society. But in any case, we see this very rapid development in this area of sustainable chemistry. One possibility, talking about solvents, is the use of safer solvents, and many groups in the world are trying to use water as the reaction medium. Water is, of course, abundant and clean and cheap. And nevertheless, there is some concern that once you use water and you contaminate water, then it may be very difficult to purify and recover clean water. But in any case, there is a lot of interest in the use of water as reaction medium, and also about the use of ionic liquids, in the sense that ionic liquids have a high boiling point. In other words, they are not volatile. So in this regard, it's more difficult, to contaminate the environment when you use ionic liquids. Also, there is a potential use of supercritical or fluids that are prepared, for example, from carbon dioxide. And then today, as I said, I will be talking about the possibility of doing reactions, carrying out reactions in the absence of solvents. So Professor Sheldon has said the best solvent is no solvent at all. So that's a possibility. And then, as I said, the use of alternative, efficient, perhaps more efficient energy sources. And in this regard, one can use microwaves. In the last years, we also have seen many laboratories acquiring microwave ovens to speed up reactions and so on. But today, I will be talking about the possibility of using mechanical energy that many times turns out to be also more economical. And then, actually, the combination, doing reactions in the absence of solvents and using mechanical energy to activate those reactions. And we have seen, of course, for many years, emblematic for chemistry and pharmacy, the use of the mortar and pestle. More recently, at industrial scale, we have seen these very large ball milling equipments, and in the laboratory, the development, let's say, for the last 2 decades or so, of such vibrational, let's say, this horizontal type mechanical ball milling, controlled electrically, let's say, and also this kind of planetary ball milling equipments. How many of you have a ball milling apparatus in your laboratory? Some of you. Okay. It's of course used also in materials chemistry, and very well. For those of you who have not seen it, I have this very short video. The idea, as I said, is to carry out the reactions in the absence of solvents. So we see, in this case, a stainless steel container. One adds starting materials, no solvent is used, and then perhaps you saw there is, in this case, one ball also of stainless steel, and then the vibrator produces this energy, mechanical energy, that is able to break up bonds and create new bonds. And in that sense, at the end, what you have is the product. And in the absence of solvents. An important reaction in chemistry and biochemistry and the biological area is, of course, the formation of peptide or peptidic bonds, for example, from two amino acids, the possibility of forming dipeptides and then, let's say, a longer peptidic chains, and eventually even, let's say, proteins or however, always a problem is the activation of the carboxylic group. So under normal conditions, this condensation between the carboxylic group in one amino acid and the amino group in the second amino acid is not so simple, requires usually some type of activation. I am showing too much already. But anyway, I would like to mention that the very last day in December, the last day of activities anyway, for most people in our chemistry department, I was reading the journals. And one of them was this Angewandte Chemie issue. And then I saw this article by Frederick Lamartine, Jan Martinez, and co-workers, and they describe the use of a ball milling apparatus in the formation of peptides in the absence of solvents. As you see, they start with this activated form, this urethane N-carboxy anhydride of the first amino acid and a second amino acid as an ester. Actually, they use it as a hydrochloride in a ball milling apparatus, as I said, and getting the desired dipeptides in high yields. As you know, Professor Martinez, Professor Lamartine work in Montpellier. I had at the time a collaboration with a group of Professor De Winter and perhaps you know Evelina Colacino. Anyway, Evelina had showed one of these ball milling apparatus, and so when I read this paper, I saw the obvious. There is this cartoon, you know, it's a scientist from the Stone Age using a state-of-the-art instrument and looking at this object. And perhaps you cannot see here, but he says, it's a mammoth. It's a mammoth. So, as I said, when I saw Lamartine's paper, I saw the obvious. We had been working with beta amino acids for some time, and so I had the idea, well, why don't we simply use now the activated form, not of an alpha, but of a beta amino acid, and we can do reactions either with alpha or beta amino acids in order to get alpha beta or beta beta dipeptides. As you know, beta amino acids or beta peptides are not natural. However, groups like, for example, the one of Professor Sebag and some others have shown that peptides containing beta amino acids instead of alpha amino acids present some interesting properties, such as more resistance to enzymatic hydrolysis. So anyway, the synthesis of such unnatural derivatives of peptides containing beta amino acids is still of interest. And so Gregorio Hernandez had to prepare such activated forms, those UNCA derivatives of beta amino acids, such as beta-alanine, or we were interested in preparing some chiral, let's say enantiomerically pure, activated forms of beta amino acids, and so this was another goal in the project. And for this, one may use this strategy developed also by the Martinez group. And as I said, we had been working in the area of asymmetric synthesis of beta amino acids. And so this technique or this approach developed mainly by the group of Steve Davis in Oxford shows how prochiral conjugated ester may be transformed into the desired beta amino acid precursor in a stereochemically or configurationally pure form, so that eventually, after hydrogenolysis, one can get the desired chiral and enantiomerically pure beta amino acid. And then with this enantiopure beta amino acid, using, let's say, traditional chemistry, one can form the desired UNCA, this urethane and carboxy anhydride activated form of the beta amino acid. I have to tell you that really the very first reactions we tried was with the mortar, you know. But of course the energy that, of course, the different men or women, you know, using is different. Anyway, it's not so reproducible. But at the very beginning, then turns out, I don't know if you have seen such amalgamator. It used to be employed by dentists, you know, the odontologists, to prepare amalgams for our teeth. And however, then those amalgams were no longer used. They were replaced by resins. Anyway, my dentist actually had one of these apparatus in her office. She did not require it anymore, so she gave it to me. And so we really began our work using one of these amalgamators. Here you can see the holder, so the container will be here, and the vibration will be good enough. Yes, it's actually fairly accurate and so on, the frequency that you can get. And so we started work. Actually, we began using Teflon containers. There are different types of containers and balls that one can use, but this is the way we started. And the very first reaction carried out by Gregorio Hernandez was this reaction between this UNCA, this activated form of beta-alanine, and the methyl ester of alanine. So in the ball mill apparatus, at 3,800 revolutions cycles per minute, and we found that the desired product, the dipeptide, could be obtained very cleanly. I mean, really the side products are sodium chloride and CO2, and isolated yield of the desired dipeptide. Gregorio could confirm that reaction was essentially complete after 2 hours. One may mention that in solution, this kind of coupling or this kind of dipeptidic bond formation takes place usually overnight or 24 hours. So we are seeing that under solvent-free conditions, using this mechanical activation, we can get the desired product in only 2 hours. And for his PhD thesis, Gregorio had to expand, you know, the scope of the reaction. So he tried different combinations of alpha and beta amino acids as starting materials, so that he could get these combinations of alpha beta and beta beta dipeptides, usually in very good yields. So at this point, this could be me. Let me see. This could be me saying, well, starting from such substrate, we can get to the dipeptide. And there is something in the middle that is like a miracle, you know. And then you will say, well, I think you should be more explicit about it. And the reason for this question is that indeed, even from the time of Aristotle, there was already the idea that one cannot carry out reactions in the absence of a solvent. And what we are seeing here is that actually the reaction is more rapid under solvent field conditions in this ball milling apparatus than in solution. So what's happening? And one possibility or one interpretation there is part a bit of a slide missing, but the idea is the substrates, for example, the solid substances usually that are in touch, then with this mechanical energy, create a melting zone in between the solid particles, and this melted zone is sufficient so to let the reaction start and proceed. So probably you have seen sometimes when you check if substances are the same or identical or different, then you have a mixed melting point, and we find usually that different substances produce a lowering in the melting point, and probably this is happening here at the surface or the contact surface between the solid material, and this allows the reaction to start and proceed. This is another way of showing the process, in the sense that you have two different substrates, let's say A and B, and then those molecules that get in contact are allowed to react, let's say, for example, in the solid state, to afford the product in the absence of solvent. This is an experiment more from, let's say, inorganic chemistry, but you have two substrates, let's say the white and the red, and those solid materials that are in touch are able to react. The ones that are not in contact do not react. And this is by, let's say, heating slightly from room temperature to, let's say, 50 or 60 Celsius. And I'm sure it happens in France also, but in Mexico it used to be that you would talk to a potential student, and you are convincing him or convincing her to join your group, and then you are excited talking about the project, and eventually he or she says, well, but is this going to be useful? Is this going to be useful? And so Gregorio said, well, is this peptide forming reaction useful in any way? Well, it turns out that there are several dipeptides, for example, or different peptides that are biologically active. For example, carnosine is a dipeptide containing this beta amino acid segment, the beta-alanine, and also is a residue of histidine. And this has different applications. It's actually sold commercially with different applications. It's also useful in strengthening of muscles. So people undergoing therapies may be taking carnosine in order to strengthen muscles. I know, I guess in France there is no baseball at all, probably, but perhaps some of you heard some years ago of a baseball player, Barry Bonds. Any of you heard of him? Well, some of you. Well, what happens is that he had these awards and trophies and so on because he was a very good hitter, in baseball. And eventually they removed or they took away his awards because they discovered that he was taking carnosine. And presumably this was considered illegal, in the sense that he would have stronger muscles, and that way he could hit the ball harder, and farther away. But in any case, has also, the other medical applications. And so Gregorio proceeded to the synthesis of such dipeptide, again, in the ball milling apparatus, and he was able to obtain, let me see, well, the lower part is missing here also, but jokingly I say that Gregorio started the company because now I show this bottle of carnosine, but it's really a joke. But the idea is that one can prepare useful peptidic derivatives in the absence of solvent. And of course the message is, if you don't use solvent, you don't only have a cleaner process, but you also have a more economic, let's say, less expensive process, and this can give you also an advantage in a commercial world. Well, and then there is this kind of a logo about organocatalysis. As you know, the idea is to use small organic molecules as catalyst, and one of the main goals is to avoid the presence of metals, because metals in some processes are not desirable. For example, in the food industry or pharmaceutical companies, it's better to avoid even traces of metals. So, as you know, there are some early examples of the development of organocatalysis, but of course, in the year 2000, papers by List, Lerner, and Barbas, and Macmillan, of course, got a lot of attention. I still feel that a Nobel Prize in Chemistry might be given in this area, but every year I see that it's given in other areas. However, this was, of course, very, very important development. Here is the emblematic reaction here, the aldol reaction between acetone and para-nitrobenzaldehyde, catalyzed by a single amino acid, proline, and affording the desired aldol reaction, let's say with good stereoselectivity, particular good enantioselectivity. And the accepted mechanism is shown in the lower part. As you know, the condensation between the carbonyl substrate and proline affords an iminium ion, and eventually the enamine, that is the key intermediate, this being chiral, can differentiate the prochiral phases of a substrate such as aldehydes, so that this then proceeds to afford the desired aldol product with the recovery of the organocatalyst. The important sentence or statement in this paper is that proline is really acting as if it were a small enzyme. So proline is really acting as a microenzyme, and so this, of course, caught, as I said, caught the attention of many chemists. And since we had preparing some peptides under solvent-free conditions in this ball milling apparatus, then we said, well, why not to use dipeptides as organocatalysts, and in particular derivatives of proline that would contain different amino acid residues, and exploring their use in organocatalysis. Turns out that Professor Karstenborn and his group, Rodriguez and co-workers, had already reported an example of such a organocatalytic asymmetric process in a ball milling apparatus, this planetary apparatus, using proline itself as the organocatalyst. And in our case, we prepare such derivatives, again, starting from proline, protection, and then formation of the dipeptide, in this case being going through a mixed anhydride activated form, and then deprotection affording the desired dipeptides containing the proline that is required for enamine formation in the organocatalytic process. And the initial experiments by Gregorio Hernandez are shown here. So using cyclohexanone and para-nitrobenzaldehyde, using this dipeptide containing proline and phenylalanine, then indeed the aldol product was obtained. As you can see, there are two stereogenic centers being formed in the reaction, so one may get 4 stereoisomers. The initial results were promising in the sense that the chemical yield was quite high. However, the stereoselectivity was quite modest. For example, a 2-to-1 diastereomeric ratio or low enantiomeric excesses. But Gregorio then looked for the conditions to optimize the reaction, modifying the concentration of the catalyst, the reaction time, and reaction temperature, finding that when he carried out the reaction at -20 or so Celsius, then the yield of the reaction was good, and both the diastereo and enantioselectivity were also quite good. The scope of the reaction was expanded or explored, as seen in some of these examples here, and especially with cyclohexanone, the stereoselectivities were usually quite high. One effect of water was, or a study of additives showed that the presence of water could be important in order to improve the yield and stereoselectivity of the reactions, and this effect by water was considered as a suggestion of kind of hydrophobic effect, so that perhaps then the reaction could proceed via a more robust transition state as shown in this slide. There is also the possibility of a non-bonding interaction. We looked at different residues containing different aromatic groups on the second amino acid residue, and we have indeed some evidence that such pi-pi stacking interaction may be important as well. For example, one experiment carried out by Elizabeth Machuca showed that the more electron demanding the carbonylic substrate, the higher the stereoselectivity was. So, for example, going from an electron-rich aromatic ring to electron poor and poorer, for example, this pentafluoro derivative, then the stereoselectivity and actually the chemical yield also increased fairly drastically. Well, as you saw, we began with working with amino acids, actually preparing small peptides, and then we used some of those peptides for doing organocatalyzed reactions. All of this in the ball milling apparatus. And as I showed, well, in the ball milling we have this beating, let's say, this stress by the mechanical process. And so, but the previous experiments showed that amino acids, peptides apparently survive with no problem, this stressful process. But something very surprising to me was when my former student, Gregorio Hernandez, working with Professor Bohm, reported that even enzymes could be used in the ball milling apparatus. And as I said, this was very surprising to me because it was usually one would think that the enzyme is degraded, is denatured by the beating process. However, Hernandez, Bon, and co-workers showed that resolutions, so chemo or mechanoenzymatic resolution of racemic alcohols could be carried out in the ball milling apparatus. By the way, this is more or less a symbol that is being accepted for mechanochemistry or mechanochemical processes. And in this case, the racemic alcohol is acylated, and, well, as you see, one of the two enantiomers is acylated, and the other one remains as enantioenriched carbinol. The results that Hernandez and co-workers report is that in 3 hours of this mechanoenzymatic process, 25 hertz of frequency afford the two enantiomeric products, let's say the recovered one and the acylated product, with high enantioselectivity. So these are additional examples presented by Hernandez, Bon, and co-workers, and this was published in 2016. It turns out that we had also done in collaboration with Professor Jaime Escalante, we had done some enzymatic reactions in solution, and again, coming back to beta amino acids, we had worked in the resolution of racemic beta amino acids, as you see in this slide. This was work of 2015, and again, when we saw, actually Gregorio sent me a preprint, of the paper. Well, I said, well, we have to try this in the mill. And so this work was reported in 2017. We were able indeed, and we means Mario Perez Venegas and Gloria Reyes. So they were able, using this scalp, Candida antarctica, lipase B enzyme, using the ball milling apparatus, and usually in these cases we use a so-called liquid assisted grinding. This is a small amount of solvent that is added to the container to facilitate also the process of the reaction. Presumably tiny amounts of this solvent, liquid assisted grinding, and as you see, we were able to obtain in this case, the hydrolyzed ester in good enantiomeric excess, and also the recovered enantiomeric beta amino acid ester in good enantiomeric excess as well. Relative to solution, well, one can carry out this process in reduced times, and many times I also obtain the product more enantiomerically enriched with good enantio discrimination. These are additional examples of resolutions. How am I doing? Okay. Well, I am almost finished, but you see, the thing is, whole enzyme can survive, let's say, the milling conditions, and in this particular case, being used in a resolution of chiral compounds. More recently, this was published last year, chiral amines were also resolved. And in the slide, show different examples, again, using this scalp and mechanochemistry, let's say. So one of the two enantiomers is preferentially acylated so that one can get both enantiomers enantiomer-enriched. So these are different examples. And again, one potential application of such technique is in the preparation of biologically active or pharmaceutically important chiral molecules, such as this rasagiline, that, as you see, involves the resolution of this racemic secondary amine so that one can get both enantiomers of rasagiline in high enantiomeric excess. As I said, we really did our very first experiments using a mortar. In our department, there was a very old shaker. You know, this was used at, several decades ago to prepare small pellets for infrared. And so it was sitting around, so we used that also. As I said, my dentist gave me this amalgamator. And then I approached people in our machine shop, and they prepared, we had this idea that in order to control better the temperature in the container and so on, and it never worked very well. So eventually, a few years ago, we bought one of these German apparatus. And then I would like to meet Gregorio Hernandez. As I said, he's now in the group of Professor Bon. Actually, he's a more or less independent researcher now. I don't know exactly, but he's not a professor, but he's independent, has his own laboratory, and is producing very much in the area of mechanochemistry, so very bright former student. I also mentioned the name of Elizabeth Machuca, and then Mario Perez, who is working in these mechanoenzymatic reactions. He's finishing his PhD now, and also a very bright student. And with this, I finish my presentation. I will try to respond questions that you might have.